Hello, Mary. Hello, hello. penjaga? Hah? Oh, maaf.没有啊，插这电啊。没有，他是休息太久了，没有电去，没有用它。精神呢？听一听啊，找不到位置嘞。哎，hello，剩你一个人了。Yeah. Okay, so I think we can start now. I would say I should speak more Mandarin. Is it, Ivan? Is Ivan online or not? Can online people hear? Hop. Hop up. Okay, okay. Okay, so where should we start? Should we start from the online question first? Okay. So yeah. Okay. So greeting to the online people and people here. Can everyone see others here? Or not? Cannot see. Wait, can see or not? Okay, okay. Maybe move my HDMI cable. Okay, so maybe let's start from the first online question, and then we will go on. Okay, so first question. So what is d2y dx squared derived? And y and x are functions of. Okay. So what does this mean? 这是什么意思？ Online also can react or talk. Open your mic or open your camera. We want to see you. Open your camera. Online people, we want to see you. So 这个是什么意思啊？Ask wrong 啊？Ask wrong. Maybe we settle this. How to derive? Yeah, it's the same. Okay, I'll tell you how to derive this. But what does it mean by y and x are functions of t? Meaning what? X and y live in where? R2. Okay, S in y live in R2. I give you a point. Okay, I give you a time, and then you give me a point in R2. So it's what? You will form a line in R2. Okay, you will form a line in R2. Okay or not? So you will have some parametric equation y in terms of t and x in terms of t. Okay. Trick uh, equation or function. Maybe you need some example. What example you have? What sort of example you could have? Xt equals to t and yt equals to t squared. Okay, what graph is this? What graph is this? Say my t from 0 to 1. Okay, what graph is this? What graph is this? What path is this? What's the curve? Hello. Yeah, paraboloid, right? Paraboloid. Because uh, because what? Because if you set s equal to t, y is just t squared, which is x squared. Okay, so you will get a paraboloid. It's 0 to 1. Okay, stop at the point 1, 1. And then the direction is going from 0, 0 to 1, 1. Okay, yeah, so this is a curve. Okay, so this is a curve. This is a curve. Okay, so how to get dy dx first? Okay, because d square y dx square is just differentiate dy dx with respect to x again. Okay, so first we need to get dy dx first. How to get dy dx? What do you use? Sorry, dy dt dx dt, right? Okay, so you use chain rule, right? So dy dx equals to dy dt over dx dt. Okay. Okay. So the problem is how to differentiate this thing with respect to x. Differentiate this thing with respect to x. So not that I actually don't like dy dx，我不喜欢写 dy over dx 这个东西。OK，我比较喜欢写 d over dx acting on y，这个才是对的写法。OK，我不喜欢写 fraction，因为它就不是一个 fraction，它其实是一个 operator。OK，in this sense，then 这个expression 就比较 make sense。OK，为什么我这么说？因为你可以 treat 里面的这个 fraction as 另外一个 y， sense 吗？OK OK， so what am I going to do? So 我 if I treat 这个看起来很夸张的 fraction as 新的 y， 我就直接 sub 这个 y 进入我的 variable 里面，I mean 我的 formula 里面 for first derivative。为什么？因为我把 second derivative 看成 first derivative on 一个 function。Make sense 吗？Okay, so what do I do? I put d over dt on 这个 fraction, and then over dx dt again, right? Dx dt is still the same because x correspond to the variable you differentiate. I still differentiate with respect to x. Okay, the thing that changed is the y. Okay, but this whole thing here we know how to compute. This whole fraction here we know how to compute. This is just dy dx over dx dt. Okay, yeah. Does that answer your question or not, Zhengkang? Zhengkang, sorry, move out, and this. Then how to find d over dt? What do you mean by find d over dt? D over dt is the operator. D over dt is the operator. Do you guys see? D over dt is the operator. You cannot find. Differentiate dy dx with respect to t. Okay. Okay, this is a good question. Okay, so okay, this is a good question. So you want to, so everyone can see or not? Oh, type. Yeah. So he asked how to differentiate dy over dx with respect to t. So dy dx means what? You differentiate y with respect to x. Okay. So meaning y inside y have a variable x. Definitely. Now you want to differentiate with respect to t again. So this means what? I need to express my s in terms of t. Okay. Can you do that or not? I can, right? Because both my function y and x are in terms of t. So I can do that. Okay. So let's give you this example then. Let's continue our example. Continue our example. Xt equals to t and yt equals to t squared. So what is dy dx in this case? Okay, we know that y equals to x squared. So dy dx is just 2x. But like what I said just now, I can compute this 2x from different way. I can use chain rule to compute dy dx using dy over dt over dx over dt. So let's prove this. Okay. So what is dy over dt? Dy over dt is 2t. Right. Dx over dt just 1, which is 2t. Okay. So how this 2x and 2t is related? Because x equals to t. Right. So we can change variable between x and t. So this is why our x can return in terms of t. Okay. So now we get dy over dx. There are two expressions. Either we can write 2x, either we can write 2t. So if you're gonna differentiate dy over dx with respect to t, of course you would use the t expression when you differentiate 2t, which is just okay. Yeah, so this is why dy dx will be in terms of t, because our y and x originally will be in terms of t. Okay. Then. How about the rest? Okay. Okay. Any follow-up question from online or not? If not, then we move on. Move on to the next one. So what's the next one? I think next one asked by Jingsen. Okay, move to the next one. Okay, next one. Why when okay when z equals to fxy is is differentiable at ab. Yeah, z plus as the terms of partial derivative. Is this what you want to ask, or you want to repeat your question again? This is what you want to ask. Okay. So first of all, you need to understand what does it mean by differentiable. What is differentiable line? Okay, so let me see how to address this. Okay, so one very easy thing is if it is a plane, right? Okay, I pick any point on the plane, the z won't change. Make sense or not? If I pick any point on the plane, the height. Okay, I cannot say the height. Okay, yeah, xy plane must be xy plane. So okay, so let me fix this. So if I pick any point on the plane, xy plane, okay, different way. So here y, here x. Then if I pick any point on xy plane, the z value, okay, z value of the point will change. Correct? When you are on the xy plane, z is equals to 0. Okay? Or if you stay on any horizontal plane, okay, horizontal plane, fix the height, okay, and then get a plane. Your height wouldn't change as well. Okay. So what kind of a surface? What kind of surface you will get a height change? What kind of surface? What kind of surface? You will get a height change when you move x and y. What kind of surface? Can you imagine? Yeah, I just tilt my plane. Okay, I just tilt my plane like this. Just tilt my plane. Or I would have some irregular shape, maybe something like this. Very better. Yeah, maybe like this. A surface. Okay, not sink down in the middle. It's like you have a cloth and then you put a heavy stuff in the middle. Right. So you will have a height change. Okay, when you move in XY direction. Okay. So the problem now is how to detect the height change. How to detect. Okay, how to detect the height change. Okay. So how we detect it is we make a linear approximation. If you do revision, you will see linear approximation. What is linear approximation? What is linear approximation? Third, from a plane. Yeah. Okay. At that point, that plane, yeah, form a tangent plane. Okay. Average close to what? Which point? Average close to plane. Okay. Tangent plane close to what plane? Surface. Okay. Surface. Yes. Plane and surface is different. Plane is flat. Surface is any two-dimensional surface. Okay. Yeah, right. So you form a tangent plane and your surface. Okay. So for example, for this irregular surface here, I pick this bottom minimum point, okay? And then I form a tangent plane here. Okay, I form a tangent plane here. Anyone know what's the formula for the tangent plane? And recall now. Lxy equals to LAB plus fx x minus a plus fyab y minus b. Okay, good. So we form this plane here. So note that this plane is built by fx and fy. Okay, so this is where the fx fy comes in. Okay, because this tangent plane is built using these two partial derivatives. Okay or not? maybe you will ask, this plane looks so off from this surface. You see the delta z here, the difference is so far. How am I going to approximate my surface using this plane here? Correct or not? But remember that what we care is local. We need to zoom in further, and further. It's like you are standing on the earth. The earth is round, but where you stand is flat. Okay, I need to zoom in further and further. Then you will see the flat space there. Okay or not? Of course, you can see that when you zoom out further, the approximation here become further, become not good. Okay, so away from this, we call this point AB, FAB here. Away from this point, the approximation is not good. Okay, the delta Z become very big. Okay. Okay, no. But close to the AB point here, the approximation is okay. If the surface is differentiable. So if it is differentiable, means what? You can use tangent plane, which is the linear approximation, to approximate every point nearby. Okay or not? Where the fx, fy comes in because you use fx and fy to build your tangent plane. Okay, Jingsen, any question you want to follow up? Yeah, you got a question, yeah? Oh. Okay, so definition of okay, so what's the definition of linear approximation? Okay, so what's the definition? Let me recall. What's the definition? Testing. Okay. So okay, so I think you are referring to this two words, is it? In the text. Okay. So linearization, by definitions, is just the tangent plane we talk about. So this is a linearization of f. Okay, so I need to say this is a linearization of f. Which is the tangent plane. What's linear? linear approximation means. So linear approximation means you want to approximate the point nearby using the tangent plane. You want to approximate. Okay, so here, what are we doing here? Let me write here. So what is linear approximation here? Okay, so by definition is this not equation but inequality here. But what this do is you are you are you are you are how to say this? You are trying approximate fxy using the linearization of f or the tangent plane of f. Linearization or tangent plane of f. Okay, if you cannot see this, let me show you one example. Can you get my statement? You're trying to approximate fxy using linearization of f. Okay. Okay, but I can give you example, but make sure you keep this statement in mind, because I don't want you to learn, how to say, just learn the example without knowing what you are doing, because this is what you typically do, right, in your high school. Okay, so in the university level, please learn the statement and then see why the statement is true. Okay. Okay, so let's give you an example. What's my mod? This is the mod. So this, go down here. Yeah, let me give you an example. Okay. Okay, one object we have seen before is like z equals to x squared plus y squared. Okay. Anyone remember what shape is this? What shape is this? What do you call that? Not quite a cone. I'm not sure what's that. That's the name, pretty sure. Paraboloid? Is it paraboloid? Because the two-dimensional is parabola. I think this is called a paraboloid. But there are a few types of them. Okay, but this is the shape. Okay, this is the shape. Okay, let's say we want to find linearization of f at a point 0, 0. Okay, how to find this? We have formula, right? Lxy equals to f 0, 0 plus fx 0, 0 times x minus 0 plus fy 0, 0 times y minus 0. What is this? f0, 0 is what? 0. Okay. fx 0, 0, 2x at 0. So it's also 0. fy 0, 0 is the same, 0. So you get a plane that is 0. Z equals 0. This is not the point, right? This is what? Z equals 0 is what? Is a xy plane. It's an xy plane, right? So your linearization here is the whole xy plane here. Which kind of makes sense? Okay, which kind of makes sense? Okay, so your tangent plane is like this. Okay, at the point 0, 0. So, what do I mean by, for example, let's say find linear summation of, let's say, f01. And let's say we want to find linear approximation of f01. What's the linear approximation of f01? Meaning, I need to go to the tangent plane and then find what is 01. Okay. So what is L01 here? So what is linear approximation? So this is just L01. So what is L01 in this case? Plus your Lxy is a constant function, right? So L01 is also 0. Correct or not? So you go to the plane, okay, and check where is 01, and then here is your L01. But what is F01? What is F01? 0 square plus 1 square, which is 1. Where's this point? This point is exactly on the surface. This point is 0, 1, 1. So how far is it from 0, 1, 0 to 0, 1, 1? How far is it? 1. Okay. So you can see that the linear approximation of f01 is distance 1 away, okay, from the actual point. Can you see or not? Can you see or not? But as you can see, if I move the 01 point closer to 0, 0, the difference between linear approximation and the actual point will decrease. Correct or not? Okay, let me find another point. So let's find another point. Okay, so here I put 1, here I put 2. About the third point. Okay, let's make it smaller. Find linear approximation of f0.01, much closer to 0, 0. Okay, what's this point here? L 0.01 is what? It's still 0. Okay, but f 0.01 is what? 0 squared plus 0.1 squared, you get 0.01. Okay, so what can you see here? What can you see? When I move the point closer to the origin, the difference between linear approximation and the actual point decreases. Okay. The point between linear approximation and the surface decreases. Okay. until you reach 0, 0, L0, 0, you will get 0. And then that's the point on your tangent plane. Okay. So this is the difference between linearization and linear approximation. Linearization is a tangent plane. Linearization, you use tangent plane to estimate your actual point on your surface or the f value. What do you think, Ethan? Okay. How about the rest? Let me see. So the delta Z that Jingsen talked about, is it on one of the lecture? Let me check. Where's the delta Z you have, Jingsen? Where's the delta Z you see? This delta Z? Zoom in. Is it this delta Z? This delta Z? Okay, then this is what I say just now. This delta Z here is the actual point, the difference between the actual point and the, okay, wait. So this delta Z here, let me see here. A little bit different. Wait, so where did you see the delta Z with respect to fx and fy? Because initially I thought you are talking about this delta Z. Where do you see the statement? Yeah. Next page. Okay. Where is delta Z? Where got delta Z? Are you talking about this term here? So I'm talking about the difference between these two terms. So okay, I can rewrite this equation. So I can rewrite this equation into f a plus delta x b plus delta y minus f a b equals to fx a b delta x plus fy a b delta y plus epsilon 1 delta x plus epsilon 2 delta y. And then I can set this to be delta z. So where delta z equals to f of a plus delta x, b plus delta y minus FAB. Is this what you say? Yeah. Okay. Yeah, correct. So if it is differentiable, meaning I can use the tangent plane to approximate it. It's different, right? Where's the difference? Tell me the difference. It has a epsilon 1 delta x and epsilon 2 delta x. Correct or not? Okay. Okay, good. Okay, very good. Okay, so okay, I think you guys really need a rigorous definition here. So, okay, so I can rewrite this definition here. If the limit of x comma delta y to 0, 0 of f of a plus delta x comma b plus delta y. Okay. So let me write down a statement and then we can discuss. And then this one minus of FAB. And then minus, let me call it the, call what? Okay, this whole thing should be just minus of LAB, wait, LXY, okay, over, here, the correct. Okay, so let me put it in this way here. Just lay it out. So like this, plus fx ab x plus fy ab delta y over over what? Over the length of so the length of x1. Let me see. Delta x. Okay. So what do I want to say here? So this epsilon 1 and epsilon 2, right? This is like a limit. This is like a limit. Okay. These two things is like a limit. So let me see how should I put this? So what you can see here is this first three terms here, right? This first three terms here coming from the tangent, the tangent plane, right? The tangent plane. Okay. But like what we did just now, we use the tangent plane to estimate this original point here. There will be a different. So let me go back to what we have. Let me go down. So we will have a different. So we will have a difference, you see? At 0, 0, the point 0, 0, the difference is 1. At 0 0.0,01, the difference is 0.01. Okay. But you can see that when the point get closer to 0, 0, meaning the delta x and delta y getting smaller, the value of Lxy and Fxy will get closer and closer. That's why when delta x and delta y getting to 0, meaning you get as close as possible to the point you have your tangent plane, the difference between the tangent plane, the linear approximation, and the actual point will get smaller and smaller, controlled by this epsilon. Where you can rewrite this statement here into the limit statement here. But you can see that the limit statement here have an extra thing, which is a formalization. It's just a formality. Okay, yeah. Okay. The bottom here is more rigorous. Yeah. Okay. So the extra term here exactly tells you. So you need to remember this situation that when I go closer to the point where I do the tangent plane, the linear approximation and my actual point getting closer and closer, then my surface will be differentiable. If not, your surface won't be differentiable. Okay. If this is true, then your surface is differentiable. Okay. So you can see that the linear approximation and your actual function point getting closer and closer when you move towards your point of expansion. Okay. Any question or not? Other question or anything unclear here? Yeah. Okay. Um, okay. Should we take a break or? Huh? Okay. Let's take a 10-minute break. So if you have question, send in first. I think there's one request. We want to discuss assignment question. Okay, I will discuss assignment question, and then maybe maybe I do some summary on vector calculus. Okay, I do some summary on vector calculus. I draw some comparison between line integral and surface integral. Okay, so better to help you which object you want to integrate over. Okay, so we will resume at 3 o'clock. In the meantime, you just type your question. Hey, there's a question here. So at a point, we find gradient with respect to x, gradient with respect to y, and then sum them along with the value of the of like above. Okay. Yes. When you sum them together, meaning you are finding the equation of a plane. That's right. When you sum them together, you are finding an equation of plane. Then when you add the value, meaning you shift the plane towards that point. About what? Torsion. Why ask about torsion? We didn't learn torsion. Didn't do torsion. Alright. Didn't do torsion. Where's the torsion? Okay, now, someone So, how about the Jacobian? What's about Jacobian?
找我有知道这个是
哦把它拉起来。
是这样搞，
怎么你还没有吃？
我吃了，我提了，
你吃了？
好，
那你再去买吃。
提神。
拉 place equals 一般用在什么时候啊？拉 place 对的，然后结果就是比较的，没有用，他的我们没有学，我不会的写出来，结果好像原来都是没有学，这个也没学，就是我觉得你自己看的。
读出来会的。
第一句的话，
下个谁能请我来我班。
education 的最重要的其实是在那挑对了，就直接去挑的。我们就是13、16了。
等下我会 list down
你考到什么个例子出来？
啊，
这么好啊，大考。
不是 list
这么过。还能考几道？几道？5道大题吗？看见了。6道。再拿出来看一下。
Hello. Okay. Maybe we take prime precious. We keep going first. And then someone want to ask again. We will answer again. Okay. How about go to Simon first, since Han Wei want to talk about assignment. I think this assignment you guys did pretty well, but maybe some of you copy your friend's answer or share with your friend, right? You write too close. you write too closely, and then some point are false, and then you also put the same sentence. So I took the marks off there. So if you have any dispute about your marks, you can talk to me. Okay, if you think I give your marks wrong, you can come and argue with me. That's fine. Yeah, because sometimes I will be overlooked. And then I posted out the solution already. Okay, so first question here, prove that if f is a function of two variables, then that is differentiable at AB, then f is continuous. Most of you did pretty well. And most of you did pretty well. So what do? You just get the definition of differentiability and then take the limit. And then you will see that that's the limit you want in the continuity. Okay? So differentiable implies continuous. So if you can linear approximate your surface using tangent plane, then your surface is continuous. There's no hole there at every point. At the point where it is differentiable. Okay. I think first question should be all right. Right. No question? Yeah, your definition is wrong. Yeah, check your definition. One thing I can tell you ChatGPT is like people, you know, 人云亦语. ChatGPT is doing that. 人云亦语. Because ChatGPT don't know what is the correct answer. He just assemble the language together. It's a language model. It's not a answer machine. So you need to always check what ChatGPT says. Maybe ChatGPT will get you a head start, but please don't believe it in total. It can give you a head start, but you have to verify it. ChatGPT is a language model. It's not an answer machine. Okay, or not? Yeah. So you have to go and check what's your definition. The definition we have mentioned it already just now in the class. Just now we discussed. Okay. Okay. So second, I think this is the hardest question of all. Yeah, hardest question of this assignment. So I want you to discuss about two equivalent definition of closed set. Okay. So meaning what? Meaning you want to show that the first statement is true if and only if the second statement is true. So there are two directions you want to show. So let's pick one direction. So first direction I'll pick is suppose a set contains all its bounded point. Wait, no. So suppose a set can be written as R2 get rid of some open set. Then I want to show that this particular set contains all its boundary points. Okay, let's pick this direction first. All right. So what do I write? So suppose that the closed set C is R2, removing some open set in R2. And we want to show that this C contains all its boundary points. So how do I show? So I suppose on the contrary, it doesn't contain all its boundary points. Suppose it doesn't. Okay, so this is proof technique. So in this question here, I don't require you to imagine what is boundary point, what is open set, closed set. Okay, what I want you to do is just based on definition and logic. Okay, pure definition and logic. Set theory. Because set theory is what I can ask for. because you have done discrete math. Okay, set theory. So suppose, on the contrary, C doesn't contain all its boundary points. So what happened? Let's pick such point. Okay. And then this point is in R2, but not in C. Meaning what? It must be in the open set. Remember. But I have a contradiction here. Why? Because this is a boundary point of C. Boundary point of C means what? Every this you take around the C, it must contain point in C and not in C. So meaning what? There's no this around this point such that it contains in S. But you tell me that this point is in X, and X is what? X is in an open set. Okay. Open set means what? Means what? Every point in the open set you can find this such that it completely lies in the open set. But this one you cannot, because it's a boundary point of C. So meaning this point have to lie inside C. So C will contain all the boundary points. Okay or not? Okay, because this question actually comes from analysis class or topology class. So some of you use advanced proof, use the terminology that I haven't taught before, like interior point, limit point. This is not allowed. Okay, this is not allowed because we didn't touch those concepts here. And I show you that I don't need to use those concepts to do the question. Just purely by definition. So this is a very important skill you have to acquire. Okay, when you do pure maths class. I don't care you don't continue your pure maths path, but if you're gonna stay inside pure maths class, or meaning next year, next sem, next long sem, you need to do 2 pure maths, right? In the second year, you have to do 4 in total. So in these classes, make sure you hold your definition well. Okay. Yeah. Definition is really, really important for pure maths. If not, pure maths is just nothing. Because pure maths is where we do things rigorously, very rigorous. Okay, put to complete, how to say, completely. I mean, put things under the sun. Okay, under the light, under the sun. You cannot hide anything in pure maths. You cannot hide. We have to deal with all the definition. Okay, now for this direction. For this direction, everyone okay? Yeah, I think you guys, some of you show different approach, which is okay, which is good. So pure maths is like this. So there's a lot of ways to solve one question. So when I mark your assignment, right, your working or what, as long as it makes sense, I don't care how you solve it. As long as you are using the right method. Okay. So I'm not like different lecturers say, you have to use this way, you have to use that way, right? Or you have to get the correct answer, otherwise no mark. I value the step. I value the steps. So the steps will hold more marks than the final answer. Okay or not? Yeah. If just a simple calculation error, maybe I just take off 1 or 2 marks. And then the step will hold more marks. Does it make sense? So this is about pure maths. Normally, this is what we did. Okay? Is Hanwei okay with the direction that we discussed just now? Okay. Okay, let's discuss the other direction. How about the other direction? I suppose that this closed set here contains all the boundary points. Then I need to show that this set can be written as R2 take away some open set. So meaning what? The definition said that exists. So meaning I need to find the open set for you. So what's the candidate here? The very obvious candidate here is R2 take away C. Because why? Because you want C, so because you want C equals to R squared slash X. X is the unknown. So meaning what? You just take X equals to R squared slash C. Why? Because if you do it this way, R squared slash C is what? It should be C. Okay. Yeah. Okay. So once you pick this, try and show that this thing is open. Okay, how to show that this thing is open? For every point, you need to be able to find and open this. But I don't know what is C. So what can I do is, I again use contradiction. Suppose X is not open. If X is not open, what happens? There exists, there's a typo here. There exists a point A, B such that for every A and B, so that for every open disk around AB, B doesn't contain in X. It doesn't contain in X, meaning what? It has some point in X and not in X. Surely it has some point in X, right? Because AB is in X. Then it also has some point not in X, because I say that it doesn't contain in X. So meaning what? So actually this point is the boundary point of C. But we say that C contains all its boundary point. Okay, so this cannot be the point in your complement. Okay, so this is a contradiction. So just now I talked about you cannot imagine what closed set is it. So some of you use my lecture example. So closed set maybe is a closed interval or closed ball. So those are just particular example to this statement here. Okay, I want you to show in general. Why is it true in general? So this is how you make pure maths intriguing, right? You don't need to go down into example and then show one by one. You show by proof. I don't even know how the closed set looks like. Okay, whether is it a closed interval or not, a closed ball or not, and then I can show the statement is true. So this is a nice thing about pure maths. This is proof. Okay. Of course, you cannot say I just know how to prove. I don't know how to do example. You need to keep both in your mind. But I want you to go another level. You know example. Why is it true in general? You need to do it. You cannot tell your boss, hey boss, this word. Later your boss asks you, only this case work, how is it work in the different cases then? Prove it. You need to prove that this is true for all the cases. Correct or not? This is how you apply your pure maths. Okay, it's very hard. It's very hard. But this is what you need to learn. Okay or not? Okay. Any question before we move on? You got a question? No? Since you asked this, yeah. About what? Is it long or we discuss later? Discuss later, okay. Just discuss personally later. Okay. But do you understand what am I doing? Okay. Right. Okay. Question 3 is quite straightforward. You just need to check the stationary point. There's no singular point here because this function is differentiable. And then check the boundary point, right? And then you compare which one is the maximum, which one is minimum. And maybe one point I want to comment here is the question asks you to find abstract values, not just point. Okay, don't just give points. You need to give values. You need to evaluate the points. Okay, not? Yeah. Okay. Next one, question 4. Yeah, 4 here. I think there's 2 or 3 of you solve this without advanced technique. What you do is you just do plain integration. So you need to realize that integration domain here is actually part of part of a circle, part of this, so that you can use polar coordinate to to integrate. Okay. Actually, last class I have one of them success without using polar coordinate. They just do the change of variable and then they do it for 2 pages, I think. And then there is success, which is quite amazing. But if you just use polar coordinate, you just need maybe 4 or 5 lines and then draw a picture is enough. Okay? Yeah. Okay. So in this class, whenever you see double integral, triple integral, make sure you draw the integration domain and then see which coordinate is better to use. Okay, drawing is very important in this class. Okay, last one, question 5. Asks you to compute this integral e to the minus x squared from negative infinity to infinity using a triple integral. So in class, we did double integral. So now I ask you to upgrade another dimension. Okay, see if you can show that this integral here equal to square root pi or not. Okay. Some of you get wrong answer, but somehow you didn't realize. Because in class we already showed that this integral is square root pi. So you have to at least make sure your final answer is square root pi. Right. So there are 2 ways to do this. You can use spherical or cylindrical. Actually, cylindrical is easier. But when I first thought about this, I do it in spherical. So I write down some spherical steps. Then mostly it's just integration technique using spherical coordinate. So make sure you use the right Jacobian factor when you do change of coordinate. Actually, change of coordinate is some form of change of variable, right? And then when you change of variable, there's something that drop out. The things that drop out is the Jacobian factor. Now you learn it. Okay, it's the Jacobian factor. Okay, now, any question regarding assignment 3 or your marks? I think this time the average is quite high. Yeah, I think most of you get 35 and above, around there. Quite a few get full marks, almost full marks. Yeah. Hey, wait, slow how? Oh, is it? Drink coffee and then. What's that? Chocolate cake. Chocolate cake. Yeah. Any other question? Or you want to do summary on vector calculus? Have you guys tried enough exercises on vector calculus? Or you want to go through some exercises again together? Not again, I mean, those I haven't done in the lecture. What do you think? Some summary and then do some question together. Okay. Okay. You can pick question for me later, or I pick some question. So let's do some summary on vector calculus. Or before that, anyone want to ask question before doing what I wanted to do? Okay, let me do summary on the vector calculus first, and then we will do, before we leave, we do a final summary for go through what we have learned. What's the topic we have learned that you should study. Okay. Okay. Okay, right, huh? Okay. Right. So, so let me draw some line here. So what's the main thing we have learned in vector calculus? So there are few objects you need to keep in mind first. One is scalar field, one is vector field. Okay, what is scalar field? Typically, we write it as small f. Vector field, we write it as a big F. What is vector field? It's a function from R3 to R. And then, what is vector field? It's a function from I to Rn. So in our case, we take small dimension R3 to R3. So how to get this vector field? Actually, this vector field, you can build it using scalar field. Okay, F1, F2, and F3, for example. 3 of them. Right. Because 1 little f gives you R. So I need 3R to give me 3 number in R3. Okay, so this is the thing you need to keep in mind. Example, you want example? Okay, so let's look at one example. For example, f x, y, z equals to x, for example. Right. You give me 3 number, I give you 1 number. How about big F? For example, x, y, z, like this. But normally in the lecture note, you will see like xi plus yj plus zk like this. It's similar, they are the same. Okay, same presentation. Okay or not? Yeah. Or sometimes you see it as a row vector like this, x, comma, y, comma, z. It's the same. These 3 things are all the same. Okay. So please keep in mind, scalar field. What is scalar field? Give me a point, I give you a number. Vector field, give me a point, give you a vector. So this is suggested by the name, scalar and vector. So the codomain is a scalar. Codomain of vector field is a vector. Codomain of a scalar field is a scalar. So field, why is it field? Because our point is like, you can imagine that you are running on the football field, right? The point on the football field. Okay. In a plane, in a field. because this is physics term, so they imagine it like that. Okay. Okay, so how are we gonna play around with this scalar field and vector field? So two main things we introduce in vector calculus. So one is called the line integral. One is called the surface integral. Okay, so let's talk about one case first. Line integral of a scalar field and surface integral of a scalar field as well. Okay, let's compare these two things. So what's the picture you have to have in your mind when I talk about line integral? So you need to imagine there's a line running in the space. Okay, what's the scalar field? Scalar field you can imagine as a surface. Right? You can imagine it as a surface. For example, can I imagine as a surface? Yeah. So if I do this surface, right? So maybe it has a mountain here, fx1. Okay. So what's the line integral here? I compute the area above the line. It's like the area of last time we called it a curtain. So to do this, what do? We need to parameterize our curve. Okay, we need to parameterize our curve. So I need to parameterize our curve, call it RT, right? And then we have some domain for my T, A from B, finite domain. So what's this line integral here? It is integrating over the curve of what function? The scalar field, and then the change in your length, change your length. But you see, this integral here is not the usual integral we know, right? We need to do it on real number, on the real axis. Correct or not? This curve is like curvy. How to do integral? Okay. So what we do is we evaluate this integral using the parameterized curve. So you can think of it as I make the curve straight. Okay, I pull it straight so that I just use the time domain to integrate it. Okay, but imagine your time is just b minus a, but your curve is like curvy at this straight line time. So meaning you need to have some compensation. So what's that compensation here? So you need to multiply by r prime t dt. So this is what? This r prime t is what? First of all, this is a tangent vector, right? Oh, wait. Can I see this? So this is a slope. All right. Or okay, don't want to say this. This is a derivative of r. But what is this? This is the Jacobian factor coming from curve line. Does it make sense or not? Okay, it doesn't make sense. Let me show you one more thing, and then we can come back to this again. Maybe this will make more sense to this case here. So what's the surface integral? Again, it is a curved plane here. It is a curved plane. I want to integrate over a curved plane. Okay. So maybe I want to integrate over this part here. Right. wait. So here should we go down to here, and then go down here, and then integrate over this part, for example. Okay, so what do? We parameterize the surface as well. We parameterize the surface. Okay, such that U and V lies in some domain D. So here, what do we have? We have integral of x f d, the area. Okay, let's call it like this. But this is a curved surface. We still don't know how to integrate. Because in double integral, how do we integrate? We use Fubini's theorem. Okay, Fubini's theorem, how to use it? It is on a rectangle on xy plane. Okay, so we need to make it into a double integral over d. F evaluate at the parameterized surface, and then multiply by the area of the parallelogram or the Jacobian factor. So what's the Jacobian factor here? Is the norm of RU cross RV, and then dA. Okay. So you can see that there's extra term in both of the integral here. And then this extra term here is covering the fact that my line or my surface is curved. Okay, I need to make it straight. I need to make it flat. So there's some extra factor coming out. So here is the area of okay. It's also a Jacobian factor coming from a curved line. Okay. Okay. So the very important thing here is the formula at the back here. So if you want to calculate line integral, if you want to calculate surface integral, the thing you need to use is the right one. Yeah, is the right one. Okay or not? So to use the right one, you need to know how to do parametrization. Line parametrization, surface parametrization. So whenever you see a question, you should know how to do line parametrization and surface parametrization. Any question about this? Two. Any question? I don't know whether you have question or don't have question. You don't ask, because it's really important in my class. I doesn't work in the like how you work in different lecturer case. Maybe they don't need you to ask question because they just spoon feed you everything they want you to do. But I'm not that kind of people, and I don't think I will become that kind of people. So communication for me is very important. So I need two-way communication. So I say something, say something. You have to give me your feedback. Okay. Either you understand, either you don't understand. If you don't understand, you need to tell me which part or problem, and then we can try and solve it. The other class, they don't take my advice, so they are suffering in my class. So I hope you won't be the same, because I know that you guys are, how to say, you guys are more, I could say one thing is more obedient, and then you can understand better than them. So I really hope that you can improve yourself, learn something new. Okay, like I share to one of the my student, I say, every time when I was an undergrad, every semester after I study the maths course, right, So in first year, every sem I study 1. In second year, every sem I study 2. In third sem, every sem I study 4. So there are 2 sem in 1 semester. I said, every time after finishing 1 semester, I will go back home for holiday because there are semester break like you guys. I always go home. And I realized that I see the world actually differently. I perceive the world differently. So I mean, when I see the all thing happening, I will feel differently. I feel that I have new solution to these things. This is what I get by doing pure maths. Because if you're not gonna to change yourself, if you try to be as stubborn as you like, you cannot learn pure maths well. Because pure maths consists of different people's idea, different philosophy. So how are you gonna understand what they do? You need to first accept their philosophy first. And then only then you can learn what they are doing. Okay or not? Yeah. It's not like you just learn the step. Okay, I just repeat the step. That one is what? That one is just worker. 员工 mindset. You are worker mindset. 员工 ah. You just follow. Boss tell you what to do. Don't know why do that. This one is very dangerous. I mean, dangerous. Because if someone asks you to do something dangerous, then you don't know. Okay, this is what I wanted to say. Okay, continue. Okay, so we go one level up. Yeah, question? Yeah. No. Okay, no. So okay. So all these FRT, FRB, these are not vector. These are scalar field, right? So okay, give you an example, right? So let me give you an example. So let's keep the example just now. F x y z equals to x, right? Just now we said. And what RT are to pick? Still the same example we have just now. So we have t and t squared. Right. So this is what I mean by vector calculus combine everything what we have learned. Because you need parameterized equation, you need partial differentiation and integration. Maybe line not good. Okay, so in this case here, what is FRT? FRT here is what? F of t squared. Okay, so what is Z here? So maybe we need to decide a Z. So let's decide it to be 0. Let it line on the XY plane. So this is a parabola curve on XY plane. So F t squared 0, which is equal to t. This is what I mean by FRT. FUV is the same. Okay. Can you get it or not? So there's no vector here. It's still a scalar field. Just that we change variable, we substitute. Oh, okay. Okay, so this is what I mean by FRT. So now let's just go to the vector field. Okay, go to the vector field. Line integral of a vector field and a surface integral of a vector field. In the meantime, if it helps, right, you can open up example that I did in the line not stable here? Okay, it works now. Okay, let's continue. Okay. So yeah, wait. Okay. So what are we doing in the line integral of vector field? We have a curve like this, but we have an arrow in my space, right? So what am I computing with the dot product here is how the arrow will do the work along this curve, which is what we call work done. And what is this here? Let me put it down. So you do the similar things. It's really similar to the scalar field case. You need to reparameterize your curve again. I need to always make my curve straight. Okay. But in this case here, what happened? What is this dot product here becomes? Okay, I rewrite it. So what does this dot product here become? It becomes similarly, you integrate with respect to t, make it into one variable, f of rt dot with r prime t dt. You will notice that I also multiply with r prime t, right? Actually, there's a subtlety here. Okay, there's a subtlety here. So this part here is dot product between two vectors. Here is a vector. Here is also a vector. Okay, so let's give one example then. Give one example here. F x, y, z equals to, for example, x, y, z. Right. What is RT? Maybe we'll use the same RT just now. T and t squared. Okay. So what is r prime t here? It's just 1 and 2t. And we can fix some time. Let's say we fix t from 0 to 1. Okay. And we integrate along this curve here. Let's call this a curve of f dr. It becomes integrate from 0 to 1. F rt becomes okay. So we did something weird again. So because my curve seems to live in R2, so make it into R 3-dimensional. So I have x is t, y is t squared, z is 0, dot with 1, 2t, and 0. And then dt. And then you can do the dot product. Okay. Okay. Yeah. So line integral of a vector field becomes dot product between two vectors. So you could imagine the same thing happen in the surface integral, right? Okay, so what happened in the surface integral here? You have a curved surface, and you have a bunch of arrows on your space. Something like this. So what does this computing? So this computing the flux. So it's like how strong is the arrow passing through your surface, right? Or coming out from the surface. Coming out from the surface. Okay. So how do we compute this? Similarly, we make it flat, so we reparameterize it, so that we can use our double integral. Okay, so we make it into a double integral. df. You should imagine here we also have a vector, so we need to dot with another vector again. So what's the vector we dot with? It's just RU cross RU. And then D DA. Okay. Yeah, you go question. Again. Not necessarily. Not necessarily. No, not necessary. Depend on your vector field. It can be like small. It can be like somewhere small, somewhere big. Depend on your capital F. Depend on your capital F. Yeah. Okay. So whenever we talk about surface integral, line integral, you should imagine this kind of general object. Okay. And then what's the main thing you need to get to compute? Okay. And you can compare that with the scalar field. Actually, quite similar. The thing they use are quite similar. Okay, no. Okay. If okay, let's go on first. And the main thing is this. So we stop at this point. So which point is this? Okay. You want me to add? This could not. I complained to the GoodNote company. They haven't helped me fix about sync problem. Okay. So we stop at one point. Stokes theorem and divergence theorem. So what's Stokes theorem and divergence theorem? So I will split into two cases. One is line integral over line integral of a vector field over a closed curve. This is what we call a Stokes theorem. This is what Stokes theorem is about. The other one is surface integral of a vector field, also vector field, over a closed surface. And this is what we call a divergence theorem. This is what divergence theorem is about. Okay, so you can see that we build things out. Okay, we talk about line integral, surface integral of a scalar field, and then using scalar field, we build vector field, so we can integrate over vector field. Okay, now we integrate over a specific curve and specific surface. Okay, so first we do line integral over a closed curve. You can only do line integral over a closed curve because curve is just one dimensional. So it's a line integral. Closed surface is a surface. So you do surface integral. Okay. Okay, then this is what Stokes theorem and divergence theorem about. So let me give you a picture again. Okay. When I do maths, I like geometry. So I want to, so always my maths will involve algebra and geometry. So what is line integral of a vector field over a closed curve? So you need to get yourself a closed curve first. So you get yourself a closed curve, maybe like this. Okay. And then there are vector field in the space. Maybe like this. So what's the statement of Stokes theorem? If I do work around this curve, let's call it C. Work done. The distance, okay, fine. Pull out in your exam. Okay. So if you want to find work done over closed curve, means what? You can do the surface integral of curl of f dot with dA. So you should ask, where's the surface? Where's the surface? This surface is bound by the curve. Because your curve is a closed curve, then you will bound a surface. Where will you bound the surface? So let's call this surface x, right? And we want to parameterize it later. You ask a question or not? Will you ask a question? I have a ring. I have a ring. I want to bound a surface. There are few ways to bound the surface. Correct or not? Can you think of a bubble? You know bubble? 泡泡。你吹过泡泡吗？你吹过泡泡吗？ You have a hole, right? You put into the liquid and then you blow, right? You can imagine the hole as a boundary. The surface you blow could be big or small, right? These are all the surfaces that you could draw using the closed curve. But the statement here says, I don't care. I don't care what surface is it. I just care about the boundary. You get what I mean? I don't care what's the surface you computed for this curve f. You just use the same boundary. Okay or not? There's an example in your there's an example in your lecture notes where you computed the surface the surface integral of curve f over this surface and over the other surface like this is the same because they share the common boundary here. Okay, so let me label here x1, x2, right? So integral of x1 curve f equals to the integral of x2 curve f dot n. Why? Because they both have the same boundary, call it C. Okay or not? Yeah. So if your surface have the same boundary, bounded curve, then they have the same surface integral of curve f. Okay or not? Yeah, question?
代表这个代表这个保证因为
哪一个？
上面有个圈圈，下面这个不能代表
不能代表boundary。How to consider the line below x1 and x2? That's not right. Because if you're walking, what's the boundary? Still remember what's the boundary point? You need to be able to lift the space. You need to lift. You need to go up from the space. If you walk on here, you haven't go out yet. Okay, let me. I finished my tissue. Anyone got tissue or not? Not for sneezing, but I want to show you this boundary. Yeah, what I draw here is actually not a line. Okay, actually it's just a. Okay, let me show you. Yeah, it's a surface. Maybe a bit irregular, but you can see like it's just something I want to draw. Like if you walk down here, you ever walk up? You haven't 你还没有走出这个 surface 在这里走的时候
你是走不出的，你要走到这里，你才会走出去。所以它 boundary 是在上面这一圈，它这里都不是 boundary，因为你在这里，你在这里走路的话，你还是看不到外面的，你还是走不到外面。所以那个下来的那个东西，只是如果你这样去看它的话，它是长这样嘛，水流。Maybe but yeah， 那个不是我 point 吧，我的 point 就是它只是一个画法罢了，但是它的 shape 是这个 shape。It is, but it's just a way of drawing it. It's just a way of drawing it. Yeah. Mm.
Yeah.
Very big.
Yeah.
But the boundary part is only the open.
Correct.
So like
Yeah. You can say that. Yeah, you can say that. Yeah, you can say that. But this vector field is very special. It's curl F, not F itself, it's curl F. Where is curl F, not F itself. So this is the point there. It's curl F. No. This curl depend on vector field. Curl depend on vector field. And then you apply this vector field on the surface or on the path. Okay. Yeah. I mean, this line, Jing Shen, this line, you're asking about this line, right? This line you cannot imagine as the same as this line because this is just a cross section. I would say cross section. You know cross section? 不知道，就是怎讲，就是我把你切一半，我从这里看你是怎样长这样，我把你切这边，我看这里是长这样，所以我画这个的时候，我是把它这样切掉，但是它整体来说，应该也有这个 part。看到你看这个图，是不是也有这个 part 在？它是一个圆那种东西啊？什么？花盆叶啊，花盆波啊，yeah， OK 吗？把上面这个就是 boundary， 因为你走到这边，你出去你就出去了。Yeah. Yeah. Okay, so this is a vector field over over a closed curve. How about vector field over a closed surface? So let's finish up this example. One easiest closed surface to draw. One of the easiest one, I will draw a sphere. Okay, sphere is a closed surface, so it bounds a ball. Okay, inside here is a ball, right? If you fill in the sphere, you will get a ball. Okay, let's call it E, R2, X, Y, Z. And then surface, we also parameterize it. So let's parameterize using UV. You can see, can you notice something or not? Okay, let's see. Parameterize curve first. Can you notice something or not? When I parameterize curve, I use one variable. Parameterize surface, I use two variables. Parameterize solid, I use three variables. Right? So depend on what dimension of we call all these things manifold. Line, curve, solid, everything these things are manifold. Depend on how many dimension it is, you need to use the number of variables same as the number of dimension. Okay, line is one dimensional, so you use one variable. Surface is two dimensional, you need to use two variables. Solid is three dimensional, you need to use three variables. Okay, and then what? And then over this surface here, I also have vector field. For example, like this. Okay. 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 So what happened in the divergence theorem? We have a surface integral over a closed surface is equal to the triple integral of f dv. Yeah. But actually, it doesn't make sense yet, right? Because how we compute this dot product. So we need to make it flat, right? Make it flat. So after we making this surface integral flat, there's one variable that drops out, is the normal vector. Is the normal vector of the surface. So we need to discuss what normal vector we're going to use in these two theorems here. Okay. So remember that in the Stokes theorems, what do we say? Or Green's theorems, we say what? the closed curve must be what? Simple closed curve, positively oriented. Positively oriented means what? You need to go in the anti-clockwise direction. And how does this give orientation on surface? You would use right hand grid rule. Okay, you will use right hand grid rule. So you have an orientation going out this way, hand. Okay, using a right hand grid rule. Okay. Okay. How about surface integral? Remember, what kind of orientation we want to pick for surface? We want a durian. We want a durian here. So we want to pick a outward orientation for the surface. Okay, so this is an N, which is an outward orientation. Okay. So that's why this divergence theorem is called a divergence theorem. Why? Because if the dot product is positive, means what? The vector of the vector field will align with my orientation of my surface. Only I get positive. Right? Dot product, if same direction, you will get positive number. Yeah, opposite direction, only you get negative answer. Right? So that's why the middle scalar field here is called a divergence of f. Because the surface integral here tells you about how diverse is it, how diverse it is of the vector field on my surface. Only when they line up, the dot product will be positive. Make sense? And then the other one, why is it called curve? Why is it called curve? Because your work done is done in a circle. So if you have a work done in a circle motion, that means what? Your arrow have to push your particle in a rotational motion. So it tells you how the vector field rotate if you have a non-zero work done. That's why we call it a curve. Make sense? Yeah. Any question or not? Question? You guys meet any problem doing exercises or not? Exercises? Try it? Not yet. Must try the review exercise. Yeah, quiz 2 also have to do There's every chapter I'll give you a review exercise, right? Make sure if you don't do all of them, it's fine, but make sure you know how to do all the question type. It will test your understanding, the skill you need to know. For example, okay or not? Because the exam will contain some question type in the review question, so make sure you do it. Okay, before we finish, so let's quickly run through what we have did for the past 8 weeks or 7 weeks after midterm. Okay, so we start with partial derivative, right? Or parametric equation actually. But the main thing is partial derivative. So what have you learned? So first you learn about level curves, level surface, and then we learn about limit continuity. After limit continuity, then we can do differentiation already, which is the partial derivative. And then we find the tangent plane. That's what we started to discuss just now. What's the tangent plane? And then you can differentiate more times, which is the partial mixed partial derivative. And then you have met the Clairaut's theorem. If fxy, fyx are continuous, then they are the same. And then we do some chain rule, implicit function theorem. And actually the key part about this chapter is directional derivative. Okay, directional derivative. I'll post this. Actually posted already last lecture also, but I'll do it again. Yeah, make sure you run through my lecture notes, because my lecture notes contain what you need to know. You also can. So the most important thing about this, you want to review something? Oh, I mean, I will post this. Yeah. Next, the most important thing about this chapter is this directional derivative and the gradient vector, because we will keep using the gradient vector until vector calculus. And then maximum rate of change will be in the exam, so make sure you know. And tangent planes to level surfaces, and then maximum and minimum values, which is the assignment question, right? Yeah. And string value theorem, critical point theorem, second derivative test. This tree is like the how to say package in your calculus 1. So we do it again in calculus 2, multivariable case. Lagrange multiplier, if you want to forget, just forget lah. I also don't cover in my class. So I mean, maybe if it's helpful for some of the courses, definitely not for my courses. For now. And then I want you to think about open and closed set. Okay, I provide you the definition in the exam. So make sure you have enough example about open and closed set. In particular, read my lecture notes. Make sure you understand my lecture notes about open set and closed set, because you rarely find in the calculus textbook. Okay, just make sure you understand what I wrote in my lecture notes. So I want you to revise your definition of understanding. You know, because when you say you understand something, it is very superficial, 很表面，你知道吗？人家问一问你就不知道了，以为你知道，其实你不知道，你什么都不知道。You know how I check this？ 我是 mathematician 嘛 ，right？ I need to prove this。我怎样 prove？ 我随便问一问你，你就不知道了，你也答不出来。为什么这样做？因为老师跟我讲这样做了，我就这样做。You get what I mean? So you need to throw away this kind of mindset already. You know, you need to throw away this mindset. How to throw away this mindset？ 去找你要知道的东西。你什么不知道就去找你什么不知道。OK 吗？不要说别人跟我这样讲啊，就这样。不是，你一定要解释到你自己明白为止。That's why 我会每次问 make sense 吗 ？make sense 吗 ？Is making your own sense。明白吗 ？If doesn't make sense for you， 你就要把它变 make sense。很多问题还没有解决，就是有些部分大家都以为 make sense 了，其实还没有 make sense， 变成大家的盲区，所以大家都解不了这个问题。所以如果那个不是你的盲区，then you have to speak up。其实这边我觉得有问题啊。OK，then 我们 together look into this problem。现什么 ？OK 啊 ，OK， 不是说我告诉你这个是问题啊，你去解这个问题。No， 就是你要知道这个是问题。OK 了啊 ，make sense？OK， 是不是 Darren 每次问你们 make sense 吗？啊 ，OK， 所以真的是要 make sense， 不是他讲什么就是什么了哦，明白吗？Making your own sense， 自己的。OK， 不要人家一问你，你就不知道，我不知道。OK，next， multiple integral。OK， we start with double integral, and then we talk about Fubini's theorem because we don't know how to work with the definition. So we do Fubini's theorem. We do integral. What do we call that? Iterated integral, right? So actually, there's one part here first. So actually, we do iterated integral first. Iterated integral. And then we do Fubini's theorem. I can change order. And then I can do polar coordinate. I can do the polar coordinate. What's the polar coordinate? Can you remember or not? So I set x equals to r cos theta, set y equals to sine theta. Right. And then there's a Jacobian factor, which is, what's the Jacobian factor? Jacobian factor here is r. Okay, good. And then we do one variable out. We do triple integral. You see, that's why we do triple integral, because vector calculus we stop at triple integral, which is the divergence. So that's why we do triple integral here. So similarly, we have Fubini's theorem is just one more time than two variable. Cylindrical coordinate, what do we do? X equals to r cos theta, or we will call it rho cos theta. Y equals to rho sine theta, and then z equals to z. And then what's the Jacobian here? Is the rho. It's the same as the polar coordinate, because I did nothing to the height. How about spherical? S equals to rho, okay, sine phi cosine theta, and then y equals to rho cos phi cos theta, right? Or sine, okay, sine, correct. Okay, sine phi. Oh, correct. Because cos and sine is governing the xy plane. Okay, let me finish first. So cos and sine governing the xy plane, and then phi governing the z-axis. Then z equals to rho cos phi. Correct. Okay, and then what's the Jacobian here? Rho sine phi. Rho square sine phi. Okay, that's all. Okay, yeah, Kingston. Iterated integral, huh? Iterated integral. You don't remember? Iterated integral. So iterated integral is like the example Okay. So the example here is like integrate over a rectangular box of maybe a scalar field x, right? dA is what? This is just integrate from 0 to 1, 0 to 1 of x dx dy. Ah,
area
no, because depend on my function here, right? The function here is x. The area, yeah. What about the area?
the domain.
The domain is a rectangle, yeah, correct? It's a square this time, okay, and then enough. Oh, okay. Yeah. I mean, yeah, this domain here is a square. Yeah. So iterated integral means here. So this kind of integral is called iterated. Iterated. You know what does iterated means? You do one time, do again, iterate. Huh? Sorry? Okay, yeah, sure. Yeah. So you do the integral inside first, and then you do integral outside. And then you can keep doing it if you go higher dimensional. So it's iterated. I think we didn't mention the definition, right? Yeah. So, so one thing about this course is this course is not rigorous. So that's why sometimes you need to ask about definition. But it's also good for you. You have to discern what is rigorous, what is not rigorous, and then the thing that's not rigorous, you need to make it rigorous. Yeah, it's a very good practice. I try to make this course rigorous as I want, but we still need to make it better. You know, yeah, because if you look at a previous year notes, what they do is they just do exercise. Like I asked one of my FYP student just today. She's like before I come. So she also did Taylor's expansion. Okay, I'm not sure you know about what's Taylor expansion. We did it, right? I say Taylor expansion is like I want to estimate the function at certain point. Yeah, expand at x equals 0. Then that means around that point, when I add more polynomials, the sum of my polynomials will get closer to my function. But she don't know. She say, I just remember what's the Taylor polynomial of ex. I don't know what does it do. So I think this is kind of set lah. If your degree have a word mathematics inside it, Bachelor of Mathematics. If you say you're a Bachelor of something else you don't know, it's okay. But if you're a Bachelor of Mathematics, you don't know what's the Taylor's polynomial doing, then I think you can burn your certificate. Seriously, you can burn it. Yeah. Because, yeah, you can burn it. But I mean, we are all learning, so please learn as much as you can, as much as you like. Okay. And then there's something that we need to learn. Okay. And then, so in general, what to do? What is the Jacobian? If you have any transformation, okay, TUV, you can transform your integral just by multiply by the extra Jacobian factor here. So what's the Jacobian factor here? It's actually the determinant of your partial derivative. Okay, how you get rho square sine phi? These are the determinant of your matrix of partial derivative. Okay, yeah. And make sure at least for each topic here, you will have one example if you in your mind, you know how to do at least one example in your mind. Okay, for each things I say here, at least you do one example and one example you know how to use it, how to apply it. Okay. And then the next main thing is the vector calculus. So first thing we see is a vector field, and then gradient of a scalar field, and then and then conservative vector field. Okay, so maybe I give a bonus here. So I will have a proof about conservative vector field. So make sure you learn the proof here that I presented in the class. Okay, yeah, there's a proof question in the conservative vector field. So make sure you learn the proof that I presented in class. Question 4. No, question 4. Number 4. What we learned is line integrals on scalar field. All right. So replace this with a better one, which is a scalar field, which we have discussed just now. And then we have work done. Work done of a vector field, which is a line integral of vector field. Right. And then number 6, we have a fundamental theorem for line integral. So fundamental theorem of line integral is a generalization of fundamental theorem of calculus. You replace the f prime using the gradient. So this shows that the gradient is a generalization of first derivative. Okay, in the multiple variable case. Next, yeah, this part here. So this part here will be in the exam. So make sure you learn the proof here. How to decide something is conservative. Some vector field which is conservative. Then we talk about Green's theorem. Here we talk about Green's theorem. And then after Green's theorems, then we generalize Green's theorem to Stokes theorem, right? So to do Stokes theorem, we need to do curve first. Okay, so we need to introduce curve. And then there's some relation between curve and conservative vector field. And then we introduce divergence. Why? Because we want to do divergence theorem. Okay. Then to do divergence theorem, we again introduce surface integral of scalar field first, and then we go to vector field, and then we relate flux and divergence together. Okay. Yeah. So this is the last thing. So make sure when you do revision, make sure you check all these titles and then at least do one exercises you can do. Okay, with the definition and theorem sheets that I give you. Any question before? Yeah. Good. You happy?
What's the meaning about happy? Happy for the final coming.
I mean, if it is good, then you should be happy, right? Not good, then not happy. Yeah, that's me. Yeah. Kingston.
I mean, I don't so familiar for Green's theorem.
Okay. Uh-huh. Is it? Yeah, sure. Yeah. Yeah. So in some sense, it's computer will done that. Hmm. Hmm. Mhm.
determinant 跟 curve。
Say again. If I have a function fxy, and then
Then the curve
the curve f.
f
Oh, 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 you mean, oh, okay. Oh, okay. Oh, okay. So, okay. That one is what I said. Green's theorem can be obtained through Stokes theorem. If you, at this point, you forget about Green's theorem, that's fine, because Stokes theorem is more general. So how do I obtain using Stokes theorem? Maybe use this way. So what does the Stokes theorem tells you? So Stokes theorem says that if I have a line integral, this one too many. Okay, so line integral of vector field, which is the work done, this is equal to the surface integral of curl f of the A. So how is this two related? Okay, how is this two related? So this is related by setting f equals to PQ. Okay, this is equal by setting f equals to PQ. So why? So on the left hand side here, what do I get? I get PQ dot with dr. What is dr actually? So dr actually is change in x direction and change in y direction. So in this case here, you get p dx plus q dy. Okay, so this is left hand side. How about right hand side? What is the curl of this f here? L IJK. So what do? You need to take your del, the gradient operator, okay, cross with your vector field. But maybe you found a bit puzzling. How about the k component? What's the k component? Here is 0. I don't have work done in the k direction. But in curl f, I need a direction in k because it is in 3-dimensional. At least, I mean, for our case, it's in 3-dimensional. Okay, because if I bound a surface, this surface must have a direction. So this direction must live in 3-dimensional. So curl f is a 3-dimensional thing. So what is curl f here? I believe, let me see. Delta z can be 0, right? That's what I thought. Yeah, that's what I thought here. So delta z should be 0 also because there's no change in 0. There's no change in z. Okay. Yeah. So if you do in this case, do in this way, the only term that survive is del q del x minus del p del y, and then in the k direction. Yeah. Okay. In this case here, so you sub your curl f into your surface integral. Of del q over del x minus del p over del y. You note that there's a k here, right? But here, the k here should cancel with the other k coming from your surface. this is the n hat that I mentioned just now. Yeah, because they are all unit length one, right? So you talk together, you just get one. So the other k pop out from this dA here. This is where the n hat doing the job. And then what's this k here? So this k here is if in your Green's theorems you have a positive curve, right? And then this is your k using the right hand grid rule. Okay. if you try to attempt a textbook question, right? Textbook question is harder, so you will expect it will be more difficult because more technical. What I teach you is just what just standard question. Okay, but in textbook they will play around with this orientation, but we won't do it in my test. So make sure you know at least how to apply this definition theorem, okay, and then how to parameterize surface. That's all. We won't play trick on orientation. Yeah. There's too many things to learn. So make sure we learn the basic thing. And then the other thing can build on this basic. Right? Instead of I ask you go and play those things and then you don't know what's the basic. You know the basic, then you can build things on the top. We go a bit over time, but any question? Are you worried or not about the exam? Not worried. Yeah. Okay, I should be not worried. Shouldn't be worried. But of course, you need to study, but don't be too worried. Huh? Expected average? I think 70 and above. 70 and above. What's that? 葬送的福利没有周末是咩？我喜欢看打架的，我不喜欢看平静的。是咩 ？OK， try 我看。葬送的福利。
它里面有一句话，是你学过的东西不会背叛。
你学过的东西不会背叛你自己？怎么可能？怎么可能你学过的东西会背叛你自己？ OK，
然后途中就产生了很多故事哦。
OK，
然后就讲其中一个战斗，然后有个人害怕，有个人害怕，然后当他面对绝境的时候，他就是一直在逃跑，然后到最后被逼到绝路的时候，就是有点就爆发这样。
比如说
反击。
哦，反击 ，OK， 哎，
那边有一句话就是我比较喜欢的，
学过的不会背叛。这句话造成他反击。是啊。OK。几级哦？有几级哦？几级？啊？几级？总共有几级？
总共有几级啊？现在只出到第16。
哦，还是继续的啊。OK，葬送的福利给他。 推荐你们去看。Zeros 啊，它叫 Zeros，英文名叫吗？
英文名啊，英文名我
Maybe will have. 没有，我比较喜欢看那种热血的打架的啊，就是这个一言不合就开刀，进去去，有点血腥，有点血腥。哪一个？哪一个？哦，